Now that we have understood the fundamentals of RC and RL DC transients, let us solve some numerical examples on this topic. So, this is the first numerical in which we are required to find the expression of this inductor current IT. Here, a switch K is given which is switched on at time t equal to 0. We know that the expression, generalized expression for this current will be this one. So here I naught is the current after this switching action takes place. So in our case, this I naught I0 is equal to I at 0 plus, and since this is an inductor for which current cannot change instantaneously, this current will be equal to I0 minus. Of course, I infinity is the steady state current after this switching action has been performed a long time after that. Tau is the time constant. We know this is to be calculated as the ratio of L and R. So let us calculate these quantities in a step-by-step manner. Let us start with I0. So what I'm doing here is I'll redraw this circuit for the case when this switch was open. That is for the case when t was less than 0. So once we do it, we know that this switch was off and the circuit was already in a steady state, which means that this inductor was acting like a short circuit. So just before the switching action, I am showing this current as I0 minus, and now this is the equivalent circuit. This key of course was off. So here we can calculate this current I naught. So to calculate this current I0 minus, we see that this resistance 6 ohm will be bypassed because it is directly short circuited. So this current should have been coming from this junction, and it should have been coming from the original source 10 volt. So we can use KVL in this loop and we can calculate I0 minus. So let me write the KVL equation here. It will be minus 10 plus 2 into I at 0 minus plus 3 into I at 0 minus, and this is equal to 0. So from here we can calculate the inductor current just before the switching action was performed, and it comes out to be 10 by 5 amperes, that is 2 amperes. And because in an inductor current cannot be changed instantaneously, this 2 ampere will be the current just after the switching action, and this will be equal to I at 0. So this value is calculated, that I at 0 is 2 amperes. Now we are required to calculate I at infinity. So once again, I'll draw the equivalent circuit when the time t is tending to infinity. So under these conditions, this switch was on for a long time, and once again this inductor will act like a short circuit. So I am calling this current as I infinity. So let us analyze this circuit and calculate the value of I infinity. So this resistance 6 ohm will be bypassed because it is short circuited. So this current will come from the 3 ohm resistance. Here also we see that if we write KVL for this loop, which is I am showing with a dotted circle in a clockwise direction, the equation will be plus 3 into I at infinity. There is no element here, and this becomes 0. So here the steady state current through the inductor will be 0 amperes. Hence, we have calculated I at infinity also, and it comes out to be 0 amperes. Now we are required to calculate the time constant tau. So for that, what I'm doing is, for the circuit after time t greater than 0, I am drawing a Thevenin's equivalence. So I am assuming that the inductor is connected across the load terminals A and B. So I am removing that inductor from here, and I have shown the load terminals A and B. The original in this circuit at t greater than 0, this switch is on, so I have shown it as on, and I have deactivated this whole circuit. Now to deactivate it, we see that here there is a voltage source, so I have replaced the voltage source with a short circuit to deactivate it. So to calculate the Thevenin's equivalent resistance, I will see the resistance across these two terminals, and that will be the Thevenin's equivalent resistance. So let us calculate the resistance between A and B. Here we see that this resistance 2 ohm is directly short circuited. So the effective value of this part will be 0 ohms. So the equivalent circuit will look like this. This is 3 ohms, this is 6 ohms, and these are the load terminals A and B. Now if we see the resistance between A and B, we find that 3 and 6, they are in parallel, so RTH will come out to be 3 into 6 by 3 plus 6 ohms. So that is 2 ohms. Once we know it, we can calculate the time constant tau, which is L by R. So L here is 2 henries over the Thevenin's equivalent resistance is 2 ohms. So the time constant will come out to be 1 second. Hence, we can write the expression for IT. We have calculated I infinity. It came out to be 2 amperes plus I at 0. I'm sorry, we calculated I infinity to be 0 amperes. I 0 came out to be 2 amperes. Once again, I at infinity was 0, e power minus t, and tau came out to be 1 ampere, 1 seconds. So the final expression for the current, inductor current as a function of time, will be 2 into e power minus t amperes. So this will be the final answer. Let us take another example. In this circuit, we are required to calculate the capacitor voltage Vt as a function of time t. So here we have two switches K1 and K2. This switch K1 is on before time t equal to 0, and it is switched off at time t equal to 0, which is our reference time. This switch K2 was off before time t equal to 0, and it is switched on at t equal to 0. So we are required to analyze this circuit and find the expression for capacitor voltage. We know that capacitor voltage, the general expression is given like this. So V infinity is the steady state voltage. V at 0 is the initial voltage. So it can be written as V at 0 plus, and because across a capacitor the voltage cannot be changed instantaneously, this is equal to V at 0 minus. So this will be V0. Tau is of course the time constant, which is equal to RC. R here is the Thevenin's equivalent resistance. So let us solve this question in a step-by-step manner and calculate these three quantities: V infinity, V at 0, and tau. So to start with, uh, I have redrawn the circuit here, and I am drawing the circuit for time t less than 0. So at time t less than 0, this switch K1 was on and this switch K2 was off. This capacitor, because this condition was left for a long period of time, this capacitor charged to whatever voltage was possible, and it is now in its steady state. So I am calling this voltage as V0 minus. Rest of the things, they are in their place as they were. So we see from here that no current can flow through K2, and in this circuit a current should flow, but now because the capacitor is fully charged, this capacitor will act like an open circuit. So if we apply KVL in this loop, we can write the equation as minus 20 plus 5, but the current is 0, so this is 5 into 0 plus V at 0 minus equals 0. So the capacitor actually charges to a voltage which is equal to 20 volts. And since the voltage across the capacitor cannot be changed instantaneously, so V at 0 plus will be equal to V at 0 minus, which is 20 volts, and this will be taken as the initial voltage V0. So V0 is 20 volts. Now let us calculate the voltage at time equal to infinity. So let us draw the equivalent circuit when this time tends to infinity. So this key K1 is off now, this key K2 is on. So let us redraw this circuit. This key K2 is on, this key K1 is off. Once again, the circuit is left so that it reaches its steady state. When this circuit reaches its steady state, no current flows through this capacitor and it acts like an open circuit. So let me call this voltage as V infinity. Right, so again let us analyze this circuit. This current 3 amperes comes from the current source. A part of it should go here. Now, when this current gets divided, there is no path to flow here. So this current will be 0. And because this capacitor is now open circuited, it cannot go here also. So what happens is no current flows in this branch. So whole of the 3 amperes flows through this 10 ohm branch. Now we can calculate V infinity by writing a KVL equation in this loop which I have shown here. Let us write the equation. I am starting from this point. So this will be minus V at infinity plus 3 into 10 and that equals 0. So V at infinity will come out to be 30 volts. Finally, we should calculate the value of tau here. We have already calculated V0 and V at infinity. We know that this tau will be equal to RC, but this R will be the Thevenin's equivalent resistance. So what I am doing here is I am drawing the circuit with A and B as the load terminals across which I have assumed this capacitor to be connected. So the capacitor is removed from the circuit, and now since this switch K1 was off, so it has no role here. Even if it is was, I can show the components here. So it was off, and we need to de-energize whole of the circuit. So voltage source is de-energized by replacing it with a short circuit, and current source is de-energized by replacing it with an open circuit. So now we should see the resistance, net resistance across these two terminals, and that net resistance will be equal to RTH. So here 5 ohm will have no role because it is open circuited branch, and here we see that if a current goes through A, the only resistance that is it encounters is 10 ohms. So here the effective resistance will be 10 ohms. So let us use all the values that we have calculated. So V at 0, we calculated it to be 20 volts, and V infinity came out to be 30 volts, and tau can be calculated as RTH into C. So that is 10 multiplied with 0.2. This will be in seconds. So this will be 2 seconds. So the final expression for the voltage across this capacitor as a function of time will be Vt is equal to V infinity, that is 30 volts, plus V at 0, that is 20 volts, minus V at infinity, that is again 30 volts, into e power minus t by tau, and tau came out to be 2. So this is voltage, it will be in volts. So Vt will be 30 minus 10 into e power minus t by 2 volts. This will be the final answer. Let us take one more example which does not have any voltage source. So we are required to calculate this current IT as a function of time t. The switch K here is turned off at t equal to 0. So before that it was on for a long period of time. Now we know that this current will be calculated in this manner. So we are required to calculate these three values: the steady state current I infinity, initial current I at 0, and the time constant tau. To start with, let us draw the circuit for t less than 0. So here we see that this key K was uh, on before time t equal to 0. So this was on, and since this circuit was left as it is for a long period of time, so this inductor will now be acting like a short circuit, and let me call this current as I0 minus, right? So in this circuit we can calculate this current. If I assume this current to be X and this current is 3 amperes, I can apply KVL in this loop, and here I see that if I write the KVL equation, I see that plus 10x comes out to be 0. So x is 0 amperes, which means that no current flows through this 10 ohm branch, and hence whole of this 3 amperes comes to the inductor. So the steady state current before the switching action took place is now I at 0 minus. So this current is 3 amperes, and this will be equal to I at 0 plus, and that will be the initial current. So the initial current through this inductor is 3 amperes. Now let us see what happens at the steady state, that is when time t tends to infinity. So after the switching action, if the circuit is remaining as it is for a long period of time, once again this inductor will act like a short circuit, and I will call this current as I infinity. This key K was turned off, so I have shown it as an off switch. Now in this circuit, we can do an analysis to calculate this current I at infinity. So this current is known, this is 3 amperes. So the remaining current will be 3 minus I infinity. And through this 5 ohm resistance, the current is I infinity. Now if I write KVL in this loop which I have shown with dotted line, the equation will be minus 5 into I infinity plus 10, the current is 3 minus I infinity, and that equals 0. So let us quickly solve it. This will be minus 5 I infinity plus 30 minus 10 I infinity, and this is 0. So from here I calculate I infinity to be 30 divided by 15 amperes, that is 2 amperes. So I infinity is also known, which is 2 amperes. So now we know I naught, I at 0, which came out to be 3 amperes, and I at infinity came out to be 2 amperes. Now we are required to calculate this time constant tau. Once again, to calculate tau, we will draw the Thevenin's equivalent for time t greater than 0. So what I have done here is this K was switch K was turned off, so I have shown it as off. I have assumed the load terminals to be AB, and I have removed this inductance from this circuit. So these are the load terminals, and I have deactivated the circuit. So this circuit only had a current source. To deactivate the current source, I have replaced it with an open circuit. Now this is the circuit using which we can calculate the Thevenin's equivalent resistance between these two terminals A and B. So here we see that if a current starts from A, it encounters 5 ohms, it comes here, and then 10 ohms, and it comes back to B. So the total resistance here will be a series combination of 5 ohms and 10 ohms. So RTH here comes out to be 15 ohms. So once we know RTH, we can calculate tau, which is the ratio of L and R. L is known, that is 1.5 Henry, and this is 15. So it comes out to be 1 by 10 seconds. Now we know these all these values, we can write the final expression for current. So IT will be I at infinity, which is 2 amperes, plus I at 0, which is 3 amperes, minus I at infinity, which is 2 amperes, e power minus t by tau. Tau here is 1 by 10. So this is current, it will be in amperes. So IT will be 2 plus 3 minus 2 is 1. So this is e power minus 10t amperes. This will be the final answer.